Hello everyone, welcome back once again to GDC Classes English YouTube channel. So dear students, as you all know, we are going to discuss again with the question paper of Gpat 2022. So in this video, we are going to have the questions from the pharmaceutical chemistry part, and this will be going to be our fourth part. Now let's start with the questions. What are the questions that you have seen in the Gpat 2022 examinations? Starting with the first question, we are having, when alkenes are epoxidized with optically active peracids, optically active epoxides are formed under the same defined conditions. Epoxidation of E-butene by peroxycamphoric acid affords unequal yield of enantiomeric epoxides. However, a similar epoxidation of Z-butene can only afford. So, what is the question demanding from you? Like, this is basically the question is very lengthy. All right, so most of you just look at the question and try to skip this question, but in reality the question is like, we are having this can be our butene that is having like both the methyl groups are present on the same side and both the hydrogens are present on the same side. So this can be a cis form as well as this can also be our Z form in which both the same polarities are on the same side. So this is the Z epoxide, this is the Z butene, and the cis form, the cis version is Z while the trans version is, so this is our E-butene, that is also known as having the same properties on the opposite sides. So when we are epoxidizing with peroxycamphoric acid, it means that we are going to having a cis kind of addition, the syn addition. It means like both the carbons valency will be freed, the double bond will be broken here, and the oxygen is going to be attached from the same side. All right, so you can see like oxygen can be attaching from the same side for the epoxidation, and same here also. So this is our cis alkene, that is our Z butene. So when we are adding the, or you can say like when we are breaking the pi bond and we are going to add some groups over this pi bonded molecule, then we are going to have, let's suppose we draw like this something, and next we are also having this methyl group here and hydrogen, and we have making a bond for the epoxidation with the peroxycamphoric acid. So this is the case that we are going to be getting. So this here we can have the one chiral carbon here and one chiral carbon here. So what are the configuration of these chiral carbon centers? So we can simply just by RS nomenclature. So we are going to have carbon. Let's look at this carbon first. So we are having oxygen, carbon, hydrogen, and carbon with attached carbon or with attached oxygen. So we can have the first priority of this oxygen atom. It means this is going to be our first priority. Second will be of this bond, third will be of this bond, and fourth will be of the hydrogen. So we are having like 1, 2, 1, 2 and 3. Moving in this direction, we are getting the clockwise direction. It means it will be going to be our R configuration, since the fourth priority is attached on the dash. So as per RS nomenclature, this is our R system, and again we are going first, second, third, fourth. So we are going in this direction, that is our opposite, since the fourth priority is attached on the dash side. So yes, this will be going to be our S configuration. So in case of that is Z-butene, we are going to get only and only a meso product, since we are having the symmetry here, line of symmetry, and we are going RS, both of the chiral carbons are having opposite configurations and it's having a symmetrical element. So yes, this is our meso compound that is seen here, that you can also be written in the like our question. Again we are going to for this we will be getting one of them as R and the second one as the S, that will be having our different configuration. So for the case of Z-butene, this is our Z-butene, we can only have our meso compound, since the configuration of both the chiral carbons will be just opposite. So we will be getting only and only meso epoxides. That is the question. That's the question. It's about the stereo reactions, reactivity of our compounds, and what are the stereo orientations that we are going to get. Since the epoxidation will only afford a syn kind of addition, the oxygen will be added to that double bonded carbons from the same side, and thus we are going to get our compound. So yes, this will be our syn addition. So yes, we will be getting a RS compound, that is our meso compound. And if we are going to have our E double bonded system, then we can have our enantiomers. Since one of the hydrogens were in the dash segment, like here we are having one of the hydrogen present on the dash, and the here hydrogen will be present on the wedge position. So the configuration will be same. Next question we are having phenol upon treatment with bromine. We are having phenol, and when we react this phenol with the bromine in presence of carbon disulfide, that is a non-polar substance, non-polar solvent. So in non-polar solvent, CH2 at 0 degree centigrade, we are going to get 4 bromophenol, 2 bromophenol, 2,4-dibromophene or 2,4,6-tribromophene. So for this solvent, we are going to get only and only our para substituted product as the major one, that is 4 bromophenol will be our major compound, major product that we are going to get. Okay, at 0 degree centigrade, we will be getting 4 bromophenol, that is 80% of the product that we are going to get will be like 4 bromophenol. Reason, there are two reasons. First, the ortho substituted, since bromine is a bulky group, so there is a repulsion between OH and bromine molecule, the steric one. First, you can have first condition. The second condition is like 2 bromophenol is also having a higher volatility, so it can be steam distilled, and thus we are going to get only 4 bromophenol as our major product. Next question we are having, identify the major product formed in the above reaction from the 4 choices listed below. We are having like here 1, 2, 3, 4. So we are having butanol, that is having a 2 substitution of methyl. So 2-methyl butanol, we are having our substrate. And then we are having KMNO4, that is oxidizing agent. So this will be going to oxidize our alcohol functionality to carboxylic group. So this CH2OH will be oxidizing into COOH group. Okay, COOH group. Okay, and we are having C2H5 HCH3. So this is our case. Now again, we have obtained butane, 2-methyl butanoic acid, right? 2-methyl butanoic acid. So these two options are wrong. Now we are having S plus 2-methyl butanoic acid, S minus 2 methyl butanoic acid. This plus minus, that is dextro or levo, can only be judged or only can be calculated via experimental analysis of, that is our optical experiments. So we cannot predict the exact configuration, is it plus or minus, and also we are not listed like what kind of configuration is this. We are having 2-methyl butanol. So we will be going only with the positive sides. We are not going to have our negative configurations. So since both are correct answers, so yes, both are correct, no doubt. It could be S plus 2-methyl butanoic acid or S minus 2-methyl butanoic acid. But for the major aspect, we are going to have only our positive answer. But both of them can be correct. Both of them are correct here. Okay. 2-methyl butanoic acid, that is oxidation of the particular that alcohol functional group can be happening here. Next question we are having, among the following organic compounds, the one that is non-aromatic, Alright, so we are having benzene, that is an aromatic system, no doubt. We are having this as an aromatic system. We are having tropylium, this is a tropylium, that is 3 pi bonds and a positive charge here. So this is our tropylium system, and for the Huckel's rule also we are having 4n plus 2 configurations. That is, we must be having 4n plus 2 pi electrons in conjugation. And before this, we can also having cyclic structures. Planar, it should be planar, and for planarity you can refer to sp2 hybridization states of each participating members of that cyclic ring. Planarity. Next we are having conjugation, that is complete conjugation should be present there, conjugation. And next we are having 4n plus 2 pi electrons in conjugation. So total number of electrons that are in conjugation should be equivalent to 4n plus 2. And now solving with this equation, we must having n is equals to 0, 1, 2, 3, 4. So and like it must be a complete number, no fractional or decimal number. So for this we are having 2 electrons in this pi bond, 2 in this pi bond, 2 in this pi bond. So we are having 6 pi electrons. So 4n plus 2 that is having 6. So 4n is equals to 6 minus 2, that is 4, n is equals to 1. So yes, this is a tropylium, and yes, this is a aromatic system. This is a aromatic system. Now we are having cyclopentadienyl anion. Again, this system also will be having, like 2 electrons here, 2 here, 2 here. So total 6 electrons. So yes, 4n plus 2 will be n is equals to 1. Same like here we are having 6 electrons. Now here we are having a free radical and a positive charge in conjugation. So radical, that means a single electron. Single means a unpaired electron. And if there is an unpaired electron in conjugation, we can never have this equation. We can never have this equation as a complete number. Reason, we are having a odd electron, so it must be 2, 3, my bad, 3, 5, 7, 9, 11, something, this kind of electrons in conjugation. So this can never be an aromatic system, and this will be a non-aromatic compound. This will be a non-aromatic system. Non-aromatic system, and yes, we have asked from the question like which of them is non-aromatic. What will be non-aromatic? Okay, so yes, D will be our non-aromatic system. Non-aromatic system. Rules for aromaticity we are having, it must be cyclic, it must be conjugated, it must be planar, that is all the carbon that are in the ring formation must be having sp2 hybridizations. Next we are having 4n plus 2 pi electrons in total conjugation. Next question we are having, identify which statement among the following is true in case of E2 and SN2. So for the E2 and SN2, both of them are having bimolecular, this is elimination, this is substitution. This is also following second order kinetics, this is also following second order kinetics. Both of them will be having transition states. So what are the options? Secondary substitutions undergo slow elimination and fast substitutions. Alright, so I guess the question is being asked from the nature of elimination and substitutions, like the reactivity sequences of 1 degree, 2 degree and 3 degree compounds. Alright, so for the SN2, we are having methyl fastest, then we are having 1 degree carbon reaction, then we are having 2 degree carbon reaction, then 3 degree carbon reaction. And for the E2 we are having 3 degree, then 2 degree, then 1 degree, then methyl. Alright, so secondary substitution, slow elimination and fast substitution. So secondary undergoes slow elimination. No, secondary, intermediate and fast substitution, no. Substitution should be very low, so this is wrong. Primary substitution undergoes slow elimination. Very true, slow elimination. And fast substitution, yes, this can be correct. Let's move to the other options as well. Tertiary substitution undergoes slow elimination. No, fast elimination, this is wrong. Primary substitution does not undergo elimination. Primary does not undergo elimination and substitution. No, it undergoes substitution very fast. So this is also wrong. So yes, B is the right answer for this question. B is the correct option among them. Okay, both of them following bimolecular reactions, second order kinetics. It's a single step reaction and following the concerted processes. In the SN2 we are getting Walden inversions and inverted configuration of our product is obtained each time. Alright, so what's the difference between SN2 and E2? SN2 reactions are nucleophilic substitution, while E2 are like they are elimination reactions. Nature, SN2 substitution, E2 is elimination. They require nucleophile, they undergoes via base. They are reacting under bases. SN2 reactions does not require base, while they require bases. Solvent type, they must be having polar aprotic solvents, while the reaction is preferred on polar protic solvents. Alright, next, factors affecting the reaction rate. For the SN2 there must be low steric hindrance. For the E2 must be having better substituted alkene as our product. Insertion of an oxygen into carbonyl compound. We are having a carbonyl compound. Let's suppose we are having this system, and if we are going to form an ester by inserting an oxygen, so this will be only happening in the presence of peroxy acid, and in presence of peroxy acid we are going to have this system, and this is our bare vinegar oxidation. It's a very simple question. The insertion of an oxygen can only be taking place in presence of peroxy acids, and the ketones undergoes this reaction, and this reaction is known as Baeyer-Wilger oxidation. This is possible for both the cases, like aliphatic as well as cyclic conditions. In both the conditions this can be seen.
Identify the product that form when two cholesterol is treated with bromine. So cholesterol means this is a cholesterol derivative of cholesterol having a nucleus of cyclopentane perhydrophenanthrin ring, sterile ring. So what will happen if two cholesterol is treated with bromine? So when two cholesterol treated with bromine, there will be a formation of 2 beta 3 alpha dibromocholesterol. Okay, how this will form? Let's see from this chemical reaction. So when a chiral center is already present in the molecule, see. So what is the chiral center? So if you will see, there is a different chiral center present over here. Okay, so when there will be a chiral center present, we know the formula is 2 to the power n. What is the formula? 2 to the power n, that is n is equal to number of isomers, n is equal to number of chiral center. When we apply this formula, so we will get number of stereo isomers. Okay, so when this stereoisomer is present, when it react with bromine, it will form a mixture of diastereomers. Okay, so example is uh, you can see when this cholesterol react with bromine, there will be a formation of 3 beta, 2 beta, 3 alpha dibromo. Okay, dibromo, and the position of the bromine is, yes, 2. We will start nomenclature from here now. 1, 2, 3. So 2, 3 dibromo. 2, the bromine is in 2 position, the bromine is in beta form, and 3 position, the bromine is in alpha form. Okay.
Next question, we are having controlled alkylation of a ketone via enamine intermediate is named as. So manage reaction is, it's a condensation reaction, addition of 3 compounds. Okay, so this is not the true for here. Robinson annulation, this reaction is for the ring formation. No, this is not the correct answer here. Bamford Stevens reaction, this is for the para-toluene sulfonyl hydrogens. So yes, this is also not the correct answer here. This is about the Stork reaction. Stark reaction. In the Stark reaction, we are seeing the controlled alkylation of a ketone via enamine intermediate formation. Via enamine intermediate formations. So yes, C is the right answer for this question. That is Stark reaction. Stark reaction. So C is the right answer. Formation of an enamine from ketone, addition of the like enamine to an alpha beta unsaturated aldehyde or ketones, hydrolysis of the enamine back to a ketone. And this is the process. We are having cyclohexanone, that is a ketone compounds. So in presence of pyridine, we are having a reaction formation, the addition reaction first here taking place. That is a ene, we are having ene and amine, and thus the reaction proceeds for the forward direction.
Now let us see the another question which have been asked in the Gpat 2022. The question they have asked, that is heme. So what is heme? We know that it is going to be present in the some type of the compounds, and which is rich in the iron. Okay, let us see the options they have given. Iron containing tetraperol, iron containing polypeptide, or copper or magnesium containing tetraperol, iron containing imidazole. Okay, anyhow option C, it is going to be nowhere it is matching, because we know that already heme means it is going to contain the iron, but only thing you need to know about that is whether it is a tetraperol or polypeptide or an imidazole moiety. So structural wise, what could be the right option? Let us see with the explanation for this. We know that heme is present is in the hemoglobin also. So if you observe the hemoglobin, that means hemoglobin is found in the RBC, right? So the protein contains the heme. Whenever the protein globin it is going to be attached to this heme, we are going to see the hemoglobin. So this heme, whenever you are going to observe the structure, means it is a porphyrin with iron center. Okay, so this is a porphyrin moiety which is having a iron center. Okay, so in this way it is going to be, this iron is deeply incorporated within the protein, and porphyrin and ferrous ions are well protected. So these porphyrin and ferrous ions are well protected. So heme, that means it is an iron with a porphyrin ring and which is a non-protein. Okay. So whenever the globin, that means globin means it is a protein, then it is attached, it becomes, that means it is equals to the hemoglobin. Heme, whenever it is attached to the globin, it becomes hemoglobin. So nitrogen atoms which are present here, you are going to see 4 types of the nitrogens are present. These nitrogen atoms of this imidazole, we know that this is an imidazole rings. So of this histidine residue of the globin which is going to be present in this porphyrin ring, which are tightly binding the protein to the heme. Okay. So thereby you are going to see the heme B, that means whenever this heme which is rich in this iron, it is going to be present as the porphyrin moiety. Okay. So if you see the options they have given, that is iron containing tetrapyrrole. Okay. So structural wise it is a 4 pyrrole moieties are going to be there. That's why option A is going to be the right option. Iron containing tetrapyrrole. Imidazole moiety is there, but tetrapyrrole it is going to be the correct one. Okay.
Next question we are having, isobutane upon bromination under the influence of ultraviolet light, UV light at 127 degrees centigrade afford the following major product. So isobutane bromination under UV, that is free radical substitution reaction since it's a butane. Isobutane, all right. So we are having CH3, C, CH3, CH3 and a hydrogen. And when we are brominating this mixture Br2 in presence of UV light in 127 degrees centigrade temperature, a higher temperature. So in this temperature we can see like this carbon is having just 1 degree hydrogens, this is also having 1 degree and 1 degree hydrogens. So 1 degree hydrogen present here, 1 degree hydrogen present here, 1 degree of hydrogen present here, but this hydrogen is a 3 degree, this is a 3 degree hydrogen. Since the hydrogen that is attached from the carbon is a 3 degree carbon, so yes, this hydrogen can be termed as 3 degree hydrogen. And for the bromination we can see like brominations are more selective than reactive orders. So for the reaction, bromine can abstract this hydrogen and show the substitution at this position, this and this. But these all three are 1 degree hydrogens, while this hydrogen is a 3 degree hydrogen. So yes, we are going to get the product that is having better intermediate stabilizations. So abstraction of this hydrogen in the radical form will be getting a 3 degree radical that is having 9 alpha hydrogens more stabilized, while when we abstract the hydrogen from this position we are having just a 1 degree like radical that is not that much stabilized respect to this. So yes, we will be getting like, we are getting N-butyl bromide, no, not at all, isobutyl bromide, secondary butyl bromide or tertiary butyl bromide. So yes, tertiary butyl bromide. So when we are attaching bromine here, we are getting a tertiary, that is a tertiary butyl bromide. So yes, D is the right answer. D will be the right answer. That is isobutyl, my bad, tertiary butyl bromide, that is tertiary bromide. All right. Next question we are having, match the statements in list 1 with their correct answers in list 2 respectively in respect to modified first law of thermodynamics and choose the correct answer from the options. We are having constant heat, that is if the heat is constant throughout the reaction, this process is known as, so this process will be known as adiabatic, that is A will be having third option. So this is wrong, this is wrong, this is wrong, yes, this is correct. Reversible process at constant temperature, that is when the temperature is constant, that is isothermal, that is first. All right, B is having one. Constant volume, that is isochoric or isometric, both of them are correct, isometric or isochoric, choric. So yes, second. All right, C is one. And constant process, that is isobaric. Where is it? All right, so C is the right answer. C will be the right answer. All list 1 and list 2 are matched and we are getting the right matching sequence in the C option. In our C option, that is isothermal process when the temperature remains constant throughout the reaction, isochoric or isometric when the volume of the system remains constant throughout the reaction, isobaric, that is pressure constant, and adiabatic, that is having the heat, there is no change in heat, there is no exchange of heat in the system.
Ethyl ketogene is a 6,7 benzomorphin derivative with receptors selected towards mu opioid ethyl ketogen is a 6,7 benzomorphin derivative with a receptor selectivity towards mu opioid receptor, delta opioid receptor, kappa opioid receptor, yeah, NOP. So if we'll talk about the question, these are basically is selective towards the kappa opioid receptor. So opioid receptor have mu kappa delta receptor that is having more activity against the more activity on kappa receptor. So ethyl ketocyclogen is a benzomorphin derivative. This is a kappa mediated opioid receptor agonist, a kappa opioid receptor agonist basically. The compound has an analgesic action and so positive ionotropic effect on the electrical stimulus of the left atrium. Along with the analgesic property, it show ionotropic property. It also have various type of behavioral in the mammalian, such as locomotion, rearing, and grooming purposes. Ethyl ketogen is a 6 derivative which have kappa receptor. Moving to the next question, the major product formed in the above acid catalytic reaction. Okay, what will be the product formed when this compound react with nascent hydrogen? What will be the product that will be formed? So if you see the structure, the product that will be formed is your this. So let's understand what is this reaction basically. So this reaction is called as Beckmann rearrangement. This is called as Beckmann rearrangement. Okay, the acid catalyze the transformation of ketoxin. This is a ketoxin. Okay, ketoxin to N-substituted amide is known as Beckmann rearrangement. The rearrangement occurs in the presence of acids, okay, including strong acid like H2SO4 or sulfuric acid, polyphosphorus acid, and acid chloride like SOCl2, ROCl, and SO2Cl. So these are the acids it can react in the presence of. The reaction may be applied to the oxime both aryl as well as alkyl ketone. It can applicable for the oxime of both aryl or alkyl ketone and cyclic ketoxime. So what is the product from? So the product name is, if you start the nomenclature from here, 1, 2, 3, 4, 5. 5 nitro, sorry, 2 chloro, 5 nitro. In position of N, you have phenyl, and will be your benzamide. Because we are covering this part na benzene ring, so we call it as a benzamide. Benzamide. This is your benzamide. Okay. So moving to the next question. In the determination of configuration of glucose, Fischer subjected arbinose to rough degradation, the 4-carbon sugar obtained by the degradation. Okay. The 4' that form is here is erythrose. Okay. And erythrose, whether it is a D isomer or L isomer. So if you will see, you will get a this isomer. So if you will see, so rough degradation is basically this is a chemical reaction which is used to shorten the open chain form of monosaccharide. Here in rough degradation, the chain length or the carbon length basically reduces in case of open chain compound. It is functionally the reverse reaction of Killier-Fischer synthesis. So what is the difference between Killier-Fischer synthesis and rough degradation? In Killier-Fischer synthesis, there will be an increase in chain. That means increase in carbon number in the what we can call open chain compound. If in case of rough degradation, the just opposite to Killier-Killian synthesis, that is reduction in carbon. The rough degradation is a synthetic protocol which is used to remove one carbon atom from the molecule of an aldose. Okay, so if you will see from aldotriose, D-erythrose is formed. Okay, D-erythrose, from D-erythrose, D-aldose, altrose, D-glucose, D-mannose. From the aldotetrose, you will form D-glucose, D-iodose, D-galactose, and D-tannose. The question was, in the internal configuration of glucose, Fischer subjected arabinose to rough degradation. The 4-carbon obtained by this degradation process, that is erythrose. Okay, next. Arabinose, from the arabinose, erythrosis, L-erythrosis. produced.
and surroundings. Next question we are having the set of specific reagents used in the above mentioned synthesis from like N-butyl toluene from N-propyl M-toluene ketone. So basically we are having this and this. So if you simply look, we are having a benzene ring, benzene, we are having methyl substitution, and we are having a chain substitution at the meta position. So yes, or like ortho meta, yes, and the change only seen like this C double bond O group is reduced into CH2 group. Okay, CH2 group. So this can only be happening due to Clemmensen reduction or Wolff-Kishner reduction. So for the Clemmensen, we are having zinc amalgam HCl, concentrated HCl. So this is the case for Clemmensen reduction reaction. And NH2NH2 in presence of base, that is hydrogen in presence of base, that is for the Wolff-Kishner reduction. So this is also right, Wolff-Kishner reduction reaction. All right, so sodium borohydride, this will be giving just alcohol. This will be reduced to alcohol. SnCl2 as a CH3CO. All right, so this is also not the right answer for this question. So it could be A or C. Both of them can be having the right answers. Both are correct. A or C, both can be correct. Like the carbonyl functionality reduces directly to its hydrocarbon derivatives in the presence of either zinc amalgam HCl or hydrogen and a base. Okay, so A and C, both of them are right answers. Both of them can be correct. Clemmensen, that is having zinc amalgam HCl, and Wolff-Kishner, that is having hydrogen in presence of a base. Next question we are having, optically active mandelic acid can be synthesized from benzaldehyde in presence of the enzyme. So this is the question that is having a biochemistry like interference as well. So this is invertin, myrosin, emulsin or zymase. So for the process of formation of mandelic acid, that is also known as mandelic acid, that is having OH, COOH. This is our mandelic acid. So yes, this can only be possible in the presence of emulsin. Emulsin, okay. So C is the right answer for this. They are related to the asymmetrical synthesis for pyruvic acid. If we are having pyruvic acid, for the pyruvic acid, if we use yeast and the reduction happens, so this reduction can leads to the formation of lactic acid. But for the synthesis of mandelic acid, the enzyme emulsin can be used, and the emulsin basically reduces the compound. My bad. This benzaldehyde is converted into first cyano compound, then followed by oxidation with to give mandelic acid. Next question we are having, the major product formed in the below reaction is, what is the major product formed here? So we are having a benzene, okay, so correct it. This is our benzene system and a furane. So we are having this is conjugated diene, and this is a dienophile. This one is a dienophile. So diene, that is conjugated diene, reacts with the dienophile in presence of either thermal or photochemical conditions. So cycloaddition reaction takes place. Basically, Diels-Alder reaction takes place, and we end up getting the cycloaddition products. So basically, we are having like these bonds get rearranged, and the cycloaddition product is we are having, in which the benzene will be attached to a 5-membered furane ring system. So this benzene is attached to from this position. So no, this is not correct. 1 2 3, no, this is not correct. All right, this is also not correct. We are having 3 systems like this. Look, we are having 1 2 3 4 carbon and oxygen. So this 5 system is directly attached with the benzene ring. So yes, this is the right answer. As you all know that only the rearrangement of pi bond takes place here, and furane is more prone for the Diels-Alder reaction, one of the only heterocyclic rings that shows majorly these Diels-Alder reactions. Okay, Diels-Alder reaction. So what happens here? This pi bond shifts to this position and makes bond from this position to this. This pi bond breaks and make bond formation from this, and this bond formation takes place at this position. So this is all that is taking place, and thus the formation of our new compound takes place. Identify the functional groups from the below mentioned options that leads to weakening of benzoic acid. So we are having our benzoic acid, the benzoic acid. All right. So as you all know, an acid can express its acidity only when it is converted into benzoate, that is after and only dissociation of proton. So this shows the acidic character. To show this acidic character, the formation of a conjugate base takes place. This is our acid. Removal of proton gets give you a like conjugated base. Now the stability of this conjugate base decides the acidic strength of this particular acid. Better stabilize the conjugate bases, more and more acidity you are going to have. So these all substituents show what kind of effect. So all, as you all know, like acidity is directly proportional to minus M or minus I groups, while inversely proportional to plus M or plus I groups. Okay, plus M or plus I group inverse. This OH is having plus M effect. Chlorine is having plus M, but it's like it's a halogen, so it's having stronger minus I. NH2 is having plus M effect. NO2 is having minus M effect. So all those groups that are having minus I or minus M effect will be having better acidity, that is having more acidic strength. So these two will be having a better like acidic strength. They are going to show this benzoic acid with a better stabilized acid. But this OH and NH2 are having plus M effect that leads to the decrease in acidity of our benzoic acid, that is having A and C. the A and C will be having less basic, like less acidic benzoic acid. The substitution of these groups leads to the weakening of benzoic acids. All those orthopara groups leads to decrease in acidity of the any acid, while the meta-directing groups increases the acidity.
The major product which is formed in the acid catalyzed reaction of, here let us see the structure what they have given. I think okay, so the products they have given, let us complete this. This is the acid catalyzed reaction where you are going to see the product. In this, if you are going to observe, what will be the answer? So some structure they have given, and in presence of the acids, okay, what could be the product they are going to asking. So this is acid, it is going to catalyze the reaction. So options they have given A, B, C, D. In this you are going to see most of the reactions, it is going to be a ketoxime chemical structure. So when acids are going to be present, how the ketoxymes are going to be converted. Okay, so this is a simple question. So if you identify what is the main mechanism involved in this chemical reaction, you can answer this question very easily. Okay, so this is actually called as Beckmann rearrangement. Okay, you are going to study this reaction as a Beckmann rearrangement. In this Beckmann rearrangement, you are going to see the acid catalyzed reactions. Acid catalyzed, whenever acid is present, you are going to see the formation, that means transformation, it is going to take place. The acids, whenever these are present, they cause the transformations of the ketoxymes. That's why I told you this is a ketoxime. Okay, ketoxime, it is going to be present. This is a benzene ring, and you are going to see the transformation of this ketoxime to the N substituted amide. Okay, how this N substituted amide it is going to be converted. So this is the formation of transformation of this ketoxime to the N substituted amide. Okay, so this double bond it is going to be converted to the keto group like this, and amide it is going to be formed. Okay, so same benzene ring it is going to be seen here also, same thing. So this rearrangement it is going to be called it as Beckmann rearrangement. So this rearrangement when it is going to occur only in presence of the acids, very strong acids, that means like sulfuric acid, polyphosphoric acid. Okay, some of the acid chlorides are also going to promote this reaction. So the reaction it is going to be applied to the oximes, where it is going to occur oximes of both aryl and alkyl ketones. Okay, so when such compounds are going to be catalyzed by any type of the acids, you are going to see the transformations of these ketoxime to the N substituted amides are going to be present. Okay. So, this is the ketoxime and you are going to see the amide containing compounds. So, this is the Beckmann rearrangement. So, what is the right option? You are going to see the D. Okay. So, this Beckmann rearrangement oxide ketoxime, it is going to convert to the unsubstituted amide. Okay. So, all this way you are going to see the same thing, but here C and D are going to similar, it is looking like, but only NO2 and Cl, the positions they have changed. Okay, you should not confuse with that. So, option D is the right answer.
Next question we are having the major product obtained, major product formed in the above acid catalyzed reaction. So we are having acid, we are having oxime. All right, it's a oxime. Okay, NOH and carbonyl group, oxime. So in acidic condition, an oxime converted into amide. This is the Beckmann rearrangement reaction. This is a Beckmann rearrangement reaction. Okay, Beckmann rearrangement in which Beckmann rearrangement reaction, and in Beckmann rearrangement reaction, this oxime groups converted into amide. So basically this shifts to this position and this goes to this in the form of double bond O. So we are having like a carbon. No, this is not the true. We are having carbon oxidized to C double bond O and the N attached to the C6H5. Alright, so this can be correct. But we are having Cl and NO2 on the opposite sides, opposite positions. So we are having Cl, no, so this can also be not correct since the substitution of these benzene rings are different. Again we are having like a C, no substitution on the C double bond O group, so this is also not the correct. We are having NO2, alright, NO2 and Cl, okay, C double bond O, N, okay, and we are having C6H5. So yes, D is the right answer for this question. D is the correct rearrangement. D is the correct rearrangement. So yes, D is the right answer, and it's a Beckmann rearrangement reaction in which under acidic conditions our oxime groups rearranges to give our amide product. The major product formed in the above given reaction, that is Paul-Knorr synthesis. So for the formation of pyrrole, this Paul-Knorr synthesis uses diketo compounds when reacts with a alpha amino ketone or alpha amino carbonyl compound. So we are having it cannot be having carboxylic group, and we are having C double bond. So N 1 2, and the second will be having methyl substitution 1 2 and methyl. Okay, 1 2 and methyl. No methyl substitution, the methyl at the first position. So this is not correct, this is not correct, and carboxylic can never be obtained. Carboxylic is not given since we are having distillations KOH. So this will be leading to the only hydrogen. So yes, A is the right answer. A is the right answer. A will be the correct answer for this question.
You are going to see the questions somehow difficult in the analysis point of view. Okay, so a lot of calculations and a lot of key points they have asked in this exam. So let us solve it one by one. When 100 ml of 0.1 molar sodium hydroxide solution is added to 100 ml of 0.1 molar acetic acid. So sodium hydroxide is a strong base and acetic acid is a weak acid. In this they have given the Ka value, that means dissociation constant, pKa, that is pKa is dissociation constant, and Ka, okay. So they have given 1.82 into 10 to the power of minus 5, and pH of the solution will be. So with the information they have given, they have asked the pH of the final solution, 100 ml of the 0.1 molar sodium hydroxide, 100 ml of the 0.1 molar acetic acid. Okay. So with this, if you see the calculation part, then we will come to know what might be the option. Actually, if you see the options also, A 8.3, B 7.0, C 3.8 and D 8.7. Okay. So by seeing the question itself, we can guess some of the answers. Okay. So basically this sodium hydroxide is a strong base. So in this you can say that strong base while adding to the weak acid, you are going to get obviously the basic pH only. Okay. So mostly you are going to see the pH that is ranging from either A or D. So in these two options you are going to get, but these two are very closely related, 8.3 and 8.7. Let us see which option is going to be the right answer, right? So given Ka value as 1.82 into 10 to the power of minus 5, and with this if you find the pKa value, that means logarithmic scales, you need to apply, and in order to apply some of the logarithmic values, just some of the tricks, because logarithmic scales you cannot do it in the exam centers, okay. So that's why some of the values you are going to remember. That means whenever you are going to see the that means these types of the values, approximately you can say that the value is approximately equal to this, the power value, okay. So pKa equal to minus log of Ka value. So in this, minus log of 1.82 into 10 to the power of minus 5. So the total, if you do this, so approximately the value which is equal to the power, you are going to get it. So in this, exactly 4.74 the value. So if you don't know 5 also, you can take it approximately, okay. And pH equal to, then the formula we know that related to the, in terms of the pKa, okay. So that is half into pKw plus pKa plus log C. This is the actual formula in order to calculate the pH, and we know that the pKw value is always 14. So by substituting these values, so this value is 7, and pKa half into pKa plus half into log C values, okay. So by seeing the equation, sodium hydroxide, it is going to be added to the acetic acid, so sodium acetate and water it is going to form. Then pH equal to 7 plus half into, what is the pKa value we got, exactly 4.74 plus half into log of concentrations, okay. So 100 ml 0.1 molar. So that's why we are going to add here 10 by 200 value, okay. And in this pH, if you solve all this mathematically, then you are going to get the value, that is 8.7, okay. So exactly if you calculate, then only you can get the answer 8.7, otherwise you may get confused with the option that is 8.3 also.
Right answer. In case of halogenation reaction of alkane, abstract of primary hydrogen yields a primary radical and abstract of secondary hydrogen yields a secondary radical. So bromine reacts with an alkane and secondary and primary radicals formations are taking place. So the above example is high reactivity and low selectivity. So for the formation of 1 degree radical, 1 degree radical and 2 degree radicals. 2 degree radical. What do you think? Which is more selective? Which is high reactive? So 1 degree shows the reactivity, while the 2 degree, if we are abstracting 2 degree radical, then it is showing like it's more selective in nature. Since it's a bromine, and bromine shows selective kind of reactions more than respect to the reactive orders. So for the abstraction of primary hydrogen will be more reactive. It shows more reactive, and abstraction of 2 degree radical will shows more selective in nature. So 1 degree is not possible. 1 degree is not possible. So we are having 1 degree is high reactivity, no. Low selectivity, no, not at all possible. High selectivity will be shown. Since it's a bromine, we are having bromine radical. So we will be going to have high selectivity while low reactivity. High selectivity, low reactivity. 1 degree radical is not going to be happening. 1 degree radical formation not going to be shown by the bromine. But yes, we will be preferring 2 degree radical abstraction for the better stabilized intermediate. High reactivity, no, not at all possible. We will be only having higher selectivity, low reactivity. So yes, B is the right answer. Like yes, selection of 1 degree is not that reactive. It's not going to show with the 1 degree radicals, but yes, it better prefer for the 2 degree radical abstraction. So yes, B is the right answer. B will be the right answer. Okay, B is the right answer. Next question we are having, identify the correct descending order of strength of nucleophilic solvents from the given listed below options. We are having trifluoroethyl alcohol, methanol, formic acid and acetic acid. Okay, so all the options are same. Okay, I guess all are having same. Okay, so let's write down the compounds. What are trifluoroethanol, methanol, formic acid and acetic acid? So first of all, we are having methanol, CH3OH. Okay, then formic, acetic, trifluoro. So trifluoro the least. Then we are having acetic, since plus I nature is present on the CH3COH group. So we are having this. Then we are having formic acid, that is HCOOH. And then we are having trifluoro, that is CF3, trifluoroethyl alcohol, CH2OH. Since we are having 3 minus I nature, so it will be having very low nucleophilic strength. We are having no substitutions, so we carboxylic. Then we are having a plus I nature group. Again, we are having a plus I nature group. We are having both of them as plus I, but this carboxylic is a slightly resonance stabilized, but here no resonance is present. So the best nucleophile is going to be our methanol. Then we are having acetic acid, methanol and acetic acid, wrong, methanol, formic acid, no, wrong, methanol, acetic acid, followed by formic acid, okay, formic and trifluoroethyl alcohol. D is the right answer. D is the right answer. Okay, so we are having minus I nature groups, no substitutions, like hydrogen is showing neutral. We are having plus I, but this is like, okay, methanol will be here, acetic acid will be here, since you can see this is methanol. Okay, this is the methanol, but there is exchange of the groups, exchange of the structures just above methanol and acetic acid.
Let us move to the next question. According to the n plus 1 rule, what would be the multiplicities of the signals in the proton NMR spectrum of 1,1-dibromoethane? 1,1-dibromoethane, they have given the molecule. In this, just they are asking, according to the n plus 1 rule, what might be the splitting of the peaks. Okay, so number of signals means, if you observe for this 1,1-dibromoethane, so if you see the chemical structure 1,1-dibromoethane, CH3 CHBr2, 1,1-dibromo. Okay, so 2 bromine molecules are there and ethane, that means only 2 carbons you are going to see. So with this, if you observe here 3 hydrogens and here only 1 hydrogen. Okay, so according to these 3, you are going to see the non-equivalent proton, that is here 1 hydrogen. So there are 2 types of the hydrogen here you are going to observe, A type hydrogen and B type hydrogen. So automatically you are going to see the number of signals as 2, but those signals are according to the n plus 1 rule, how the splitting is going to be observed, that's what they have asked. So n plus 1 rule if you apply, so these 3 hydrogens are equivalent hydrogens, right? Because if you see this 1,1-dibromoethane, okay, so CH3, then bromine, 1,1-dibromoethane, right? So this is the chemical structure 1,1-dibromoethane. So let us say this is A type hydrogen and this is B type hydrogens. That means these 3 are equivalent and this is a 1 single hydrogen you are going. So number of signals will be 2. So these 3 hydrogens are going to give you 1 signal and that is 1 more signal. But according to these 3, only 1 neighboring hydrogen is there. So according to n plus 1 rule, n is nothing but the neighboring hydrogens, right? So 3 hydrogens here you are going to see. So for this, only 1 neighboring hydrogen, 3 plus 1, 4. Okay, so splitting you are going to see, that is quartet. Then if you consider this hydrogen, then according to this hydrogen, these 3 are equivalent. Okay, so you are going to observe the only for 1 hydrogen n plus 1 rule, that means only you are going to see the options, let us see quartet and doublet. Okay, so this is because 3 hydrogens are equivalent one side and 1 hydrogen is a neighboring hydrogen. For that purpose 3 plus 1 you are going to see the quartet signal, whereas corresponding to the 1,1-dibromoethane 1,1, that hydrogen you are going to see the doublet. Okay, because these 3 hydrogens will give only 1 signal, that's why. I think you have understood. Now let us move to the next question. According to Moore method, the silver nitrate solution can be standardized against the primary standard grade. Very simple question. Argentometric titration. So silver nitrate, whenever we are going to use, majorly you are going to use the primary standard material, that is nothing but the sodium chloride. So what are the options they have given? Sodium carbonate, sodium chloride, sodium hydrogen carbonate, sodium metabisulfate. Very direct question it is. So option B is the right answer. And we know Moore's method, silver nitrate, whenever sodium chloride it is added, silver chloride plus sodium nitrate it is going to be formed. And chromate, potassium chromate, it is going to be used as a indicator. So thereby you are going to see the silver chromate as a brown color precipitate you are going to observe at the end point. Okay, and Morse method, the pH range, it is going to be in and around 6.5 to 10.3 only, because Morse method is applicable for the direct method of the titrations. Okay, so mostly in the determination of the chloride ions and the bromide ions, we are going to use this Morse method, but the sample should be in the neutral condition. Okay, yeah. Now let us see the next question, that is the potential at the equivalence point for a redox reaction. They have given a redox reaction here and the potential. So mostly you are going to see, by seeing the options you can say that the question is related to the Nernst equation. Okay, option A, they have given one equation, A equal to E plus B E1 naught plus B E2 naught plus, divided by A plus B, and option B, E naught plus 0.0, sorry, decimals have missed, I think so, 0.0592 by n into log Q. Same, these two are going to be similar, but only the log of reduced ions divided by oxidized ions. And D option, E equal to E1 plus E2 divided by 2. Okay, so what they have asked, that is the potential at the equivalence point for a redox reaction. Any redox reaction, if you see the equivalence point, whenever we are going to observe, then it is going to be based on the stoichiometry only. Okay, so let us see in detail about this question, because somehow if you understand the Nernst equation also, but we have not seen in the some of the textbooks. Okay, so that's why let us see in detail about this question. So to evaluate any redox type of the titration, we need to know the shape of the titration curve. So normally in the acid base titration or complexometric titrations, the titration curve shows how the concentration of the hydronium ions or any type of the indicators, PM indicators. Okay, so like that you will come to know. Then, but for a redox reaction, any type of the redox reaction, that means both reduction as well as oxidation are going to happen. So it is convenient to monitor the titration reactions instead of the concentration of the one of the species. Okay, we should have a knowledge which ions are going to be reduced, which ions are going to be oxidized. So Nernst equation, whenever we are going to use in the potentiometry, this Nernst equation relates a solution potential at the concentration of the reactants and the products, right? So in the redox reaction also, these two are very, very important. So let us say if A and B, two reactants are there, so this is going to be a reduction type and this is going to be oxidation type, then B gets reduced and A gets oxidized. Okay, so where A ox, that means this one oxidized molecule, that is the titrant's oxidized form. Okay, actually it is a reduced analyte, so afterwards it is going to be an oxidized form you are going to see, and B reduced form is a titrant's reduced form. So the reaction potential, whatever you are going to see, E reaction, it is a difference between the reduction potential for each half reaction. Let us see how this half reaction we can write. That means whenever this reaction, complete reaction we are going to see, that is the difference between the potential. Okay, so this is how we are going to represent the difference. That means the potential for the total reaction equal to the potential for the oxidized form as well as reduced form. Okay, so the difference you are going to see, the subtraction we have to do. So after each addition of the titrant, between the titrant, it is going to reach the equilibrium state. Okay, so because the potential at the equilibrium, generally whatever the potential you are going to see, that means equilibrium has been reached, means you are going to see the end point. Okay, then the potential at the equilibrium, it is going to be 0, and the titrants and titrant reduction potential are identical. Okay, that means these two are going to be equal. So whatever the potential you are going to see for the reduced form, whatever the potential you are going to see for the oxidized form, both are going to be equal at the equilibrium point. Okay, and this is an important observation, because we can use any half reaction to monitor the titration progress, because oxidation and reduction both are happening in the same reaction, both are going to be equal. So before the equivalence point, generally what happens, the titration mixture consists of the sum of the appreciable quantities of the oxidized form as well as reduced form, but exactly at the end point the potentials are going to be equal. Okay, so the potential is easier to calculate if you use the Nernst equation. So this is going to be the Nernst equation. we know that very well how this Nernst equation is going to be helpful for calculating the potential. So, E naught whatever the oxidized form we are going to see and reduced form. Okay. So, RT by NF it is going to become under the Nernst equation, and we require some of the logarithmic scales also. Okay. So, but somehow it is difficult to calculate in the exam center for the logarithmic calculations, but we should know about the half cell reaction. That means it is how we are going to write the equation. Okay. So, for total potential for the reaction can be written as total reaction can be written. That means for this A type of the reduced form and B type of the oxidized form. Okay. So, you are going to see the reverse in the final products. Thereby, you are going to write the potential for the reaction is equal to the potential for the reduced form minus RT by NF logarithm of A reduced by A oxidized. Okay. So, actually Nernst equation whenever you are going to see, it is going to change according to the ions also. Okay. So, if you observe a clear cut idea, that means by confusion lot of oxidized form, reduced form, some of the confusion. So, in overall wise we can see the reaction that is oxidized form, that is stoichiometry here A moles are going to be there and reduced form B moles are going to be there. In the equation in the question itself they have asked. Okay. So, B it is going to be the oxidized form and A becomes the reduced form. Okay. So, in this if you see the oxidized one, it is going to taking this electrons, it becomes the reduced one. Okay. And oxidized 2 means it is going to be the electrons reduced 2, it is going to form. So, at the equivalence point all species are going to be in the unit concentration, and finally you are going to see the equation, that is the potential we are going to observe, that is the delta Z1 plus delta Z2. So, what is delta Z1? Again you need to calculate based on the number of moles and standard potentials you need to take. Okay. So, this is for the first oxidized form, this is for the second oxidized form, and total electrons based on the electrons exchanged. Okay. Total electrons exchanged if you take, that is A plus B, delta G equal to minus NF into E naught. Okay. So, delta Z naught equal to delta Z1 plus delta Z2. That means A plus B, I told you the stoichiometry. Okay. So, here if you see the equation, delta Z1 what is this? Minus A into F into E1. Same wise you are going to apply. So, what is delta G1, what is delta Z2? So, if you substitute these equations here, finally you are going to get the potential like this. Okay. Finally, the equation becomes like this. So, because somehow it is difficult to understand the question both oxidized and reduced form. Okay. Lot of abbreviations are going to be involved in this equation. So, that is why if you observe the options they have given, okay, E equal to, that means the potential for this equation, it is going to be the B E1 plus A E2 divided by A plus B. It finally it becomes like that. Okay. So, after writing the all the half cell reactions and overall wise substituting in the equations, you are going to get the equation like this. Okay. That is why option A it is going to be the right answer. Okay. Let us move to the next question. Back titration method, when it is going to be useful? Back titration method is useful for first option volatile substances, second insoluble substances, third substance for which a quantitative reaction proceeds rapidly only in presence of the excess of the reagent. Option D, substance that require heating with a volumetric reagent during the determination, in which decomposition or loss of the reactants would occur in the process. Okay, these actually seeing this 4 options are going to be the right one, right options, right statements. Okay. So, choose the correct answer from the options given below. What they have given? A only, volatile substance, that is right actually. A and C, C is also right answer, insoluble substance is also right answer. Whatever the 4 statements they have given, all are right. So, option D, A, B, C and D. Okay. So, option D it is going to be the correct answer for this question. So, back titrations are generally used in this if the analyte is volatile in the nature like ammonia, or it is an insoluble salt like lithium carbonate, or if the reaction between the analyte and the titrant is very slow. Okay, then also we are proceeding for the back titration, and it is a method where the concentration of the analyte is determined by reacting with a known amount of the excess titrant. Okay, so we are going to use the two titrants here. Titrant 1 is added in the excess directly to the conical flask, then the whatever the leftover titrant 1 it is there, that is going to be titrated with the second reagent. Okay, that's why it is an indirect titration. Okay, and back titrations, mostly these are going to be used when a back titration, how it is going to be helpful means, when the molar concentration of an excess reactant is known, but the need exists to determine the strength of the concentration of the analyte. Okay, so in such cases back titrations are more helpful, and these are going to be applied in all the types of the titrations, but mostly we are going to see in the acid base titrations. And when acid or base is an insoluble salt, then also it is going to be highly useful. And when direct endpoints are not obtained very easily, in case of weak acid versus weak base, okay, we are not finding any direct method, indicators are also may not be suitable. So in such cases you can go for the back titration, and the wherein reactions are very slow, as well as when the endpoint is easier to see with a normal titration. That means it is difficult to identify the endpoint, then we are going to select this back titration methods. Okay.
Next question. Match the list. Okay. So first is choose the correct answer from the option. So this is the buffer and this is the pH value. Okay. Now what you have to do is you have to match the buffer with the pH value. So in the option A you have HCl and KCl. In B you have HCl and potassium hydroxide phthalate. In C you have NaOH and potassium hydroxide phthalate. In D H3BO3, NaOH and KCl. What will be the pH of this? So if when talk about this HCl and KCl, so HCl and KCl is highly acidic. Please remember, this is highly acidic. Highly acidic means the pH it should be around 1.222. So option A it is 3. Next, when we talk about HCl and potassium hydrogen phthalate, okay, the HCl and potassium hydrogen phthalate, the pH range would be 2.2 to 4.0. Okay. Next is sodium hydroxide and potassium hydroxide. Potassium hydroxide phthalate is 4.2 to 5.8, and the H3BO3 NaOH KCl range is 8 to 10. So option B is the correct answer. So why like that? Let's see the explanation. So HCl, this is the strongest acid and it is produced inside our stomach with the help of which cell? Parietal cell. Okay. So this uh, strong acid, that is HCl, dissolve completely in the water, releasing high concentration of hydrogen ion, which makes the solution acidic. The pH of the solution measure the acidity or alkalinity with lower pH value, that is indicating 0.1 millimolar solution HCl has a pH around 1. If we talk about KCl, KCl is a salt form of the reaction of strong acid. When a strong acid react with strong bases, that is when HCl react with KOH, you will find KCl. Okay, KCl plus H2O. Okay, so neither the potassium ion nor the chloride ion to form hydride to react with the water, so to significantly change the pH. KCl solution is solution with a pH around 7. Okay, so some book it also varies. Potassium hydrogen phthalate, this is pH approximately 4.008. Okay, at a temperature 25 degree. Okay, in a 50 gram of solution. okay, in a 50 gram solution. It is a commonly used buffer standard for the pH measurement calibration. So this is basically used for the calibration. You know that we have a pH meter. So we have, for that pH meter, we basically use that pH meter for the measurement of a pH of particular solution. So to standardize that, so we need a strong acid or strong base to standardize that particular instrument. For that cases, this potassium hydrogen thalate or KHP, that is being used as a calibrator for the pH meter. Okay.
Now let us see the next question, that is boric acid with molecular weight of 61.83 was partitioned between the water and ml alcohol at 25 degrees centigrade. Here what they have asked, the amount of the boric acid was determined to be 0.24 grams in 250 ml alcohol and 0.32 grams in the 100 ml water. Okay. Here what they have asked, the partition coefficient of the boric acid between the water and ml alcohol. That means when calculated at the molar concentration of the each of the solution is the partition coefficient they have asked. So partition coefficient, how we are going to determine means, if you know the molar concentrations of each of the phases. Okay. Here what the two phases, water and the ml alcohol. So in water, what is the amount of the boric acid it is present, that we need to determine at the molar concentration, and in ml alcohol, what is the concentration of the boric acid we need to determine. Okay. So in that, if you see the amount, that is amount of the boric acid, already they have given as 0.24 grams. Okay. So we know that the number of moles, how we can calculate, that means mass by molar mass. So if you know this formula, you can easily understand and you can answer this question. Okay. So moles, if you want to calculate mass by molar mass, what is the mass we have already got, that is 0.24 grams. Okay. So 0.24 grams of the boric acid in water, and what is the molar mass, that is nothing but the 61.83 already they have given, and for 1 liter it is going to be the molar mass, and how much ml it is there, that is 250. Okay. For 1 molar means it is 1000 ml, but how much we have here, that is 250. So if you calculate this one, you will get a value, let us say x value. Okay. So if you want to solve this one also, you can do by calculating this, you will get a one x value, that is in presence of the water actually and ml alcohol. So if you want to calculate in the ml, this is in the ml alcohol, and in water if you want to calculate, that is nothing but 0.32 divided by 61.83 into 1000 divided by how much of the water, that is only 100 ml. Okay. So if you solve this, you are going to get the value, that is y. Okay. So this value is going to be, let us say, considered as x value, and this is going to be a y value. So x by y is nothing but the partition coefficient. Okay. We know that partition coefficient, oil in water, whenever you are going to extract them, we can determine the partition coefficient by calculating the concentrations in the each phase, oil phase or water phase. Here also they have given the water and the ml alcohol. So in each phase you need to calculate the concentrations, that means molar masses, like this. So by dividing these two, you are going to get the answer. Okay. So simply if you calculate each, that means after solving those two molar masses and number of moles calculations, you are going to get the answer, that is correct option 3.33. Okay. So this is how to calculate the concentrations in the each of the phase, thereby the ratio of those is going to be taken as a partition coefficient. Okay. So I think the question is somehow looks a little bit complicated, but calculation is very, very easy. Okay. If you solve that, you can get the answer, that is 3.33.
Next we are having our question, match the symbols in list 1 with the terms used in the list 2 of the conductance measurements. Symbols, we are having ohm inverse. So we are having ohm inverse, that is conductance. Conductance, since it's like this is a resistance. This is resistance, while ohm inverse will be conductance. Conductance. Okay. So this will be having conductance. That is where it is. Conductance. No conductance here. conductance electric. Okay, here we are having A2. A will be having second option. So all are wrong. Okay. Then this will be equivalent conductance. Fourth, B is having fourth. This kappa, that is a specific conductance. First, C is having one. This is rho, that is specific resistance, that is resistivity. This is conductivity. So yes, B is the right answer. B will be the right matching for all the given options. We are having electrical conductance, that is ohm inverse. Ohm inverse. We are having a specific resistance, or also known as resistivity, that is represented by rho. A specific conductance or conductivity, that is represented by kappa. Equivalent conductivity or equivalent conductance, that is having here right answer. Okay.
Match the list 1 with list 2. Okay, in the list 1 what they have given volumetric solutions, and in the list 2 they have given the primary standard solutions. Volumetric solutions what they have given: 0.1 molar iodine, sodium thiosulfide, sodium hydroxide and perchloric acid. Primary standard materials: potassium iodide, potassium bromide, potassium hydrogen phthalate, arsenic trioxide, again potassium hydrogen phthalate. Okay, that means 5 options they have given here, but here list 1 only 4 options. So what the question they have asked, choose the correct answer from the options given below. Okay, so in this case, if you know the exact matching of any of the two volumetric solutions, then you can easily answer this question. We know that sodium hydroxide and perchloric acid, for both these materials we can use the potassium hydrogen phthalate as a substance for standardization. Okay, so if you see the C and D, that means 3 and 5. So you can find C3 D5, that is the option you can find in the option A. So nowhere you are going to see the same matchings in the another 3 options. So automatically if you match these, let us see the A4, that means 0.1 molar iodine, the arsenic trioxide. Yeah, exactly, by using the arsenic trioxide we can standardize the iodine solution, and sodium thiosulfate we can standardize by using the potassium bromate, sodium hydroxide and perchloric acid definitely by using the potassium hydrogen phthalate. Okay, so this is the matching we are going to see exactly, and these are the different pH ranges at 25 degrees centigrade for the buffering system: hydrochloric acid as well as the potassium hydrogen phthalate, or hydrochloric acid, potassium hydrogen phthalate for sodium hydroxide. Like this, different pH ranges are going to be there. And buffering systems, if you are observing, also the volumetric solutions we can use different types of the primary standard materials, but the pH ranges are also going to be very appropriate, then only you can standardize that. Okay, let us move to the next question. So benzene theoretically can have number of possible fundamental absorption bands in the IR spectrum. Oh, the question related to the IR spectroscopy. In this, what they have asked, benzene molecule, the possible fundamental absorption bands, how many bands it can give. We know that C6H6, that is a benzene chemical formula, molecular formula, and in this if you calculate the degree of the freedom, we know that the linear molecule and non-linear molecule, whenever we are going to see, the degree of the freedom can be calculated as 3n minus 5 for the linear molecule, and for non-linear 3n minus 6. Okay, and we know that benzene is a non-linear molecule, not a linear. Okay, non-linear molecule. So fundamental absorption bands, these are the formulas we know. For linear molecules 3n minus 5, and transitional degree of the freedom, if you observe, these are 3 here, rotational degrees of the freedom 2, vibrational degrees 3n minus 5, but totally if you see the total degrees of the freedom for linear or non-linear 3n. What is n here? Number of atoms. Okay, so total number of atoms you are going to see. For a linear molecule 3n minus 5, for a non-linear molecule 3n minus 6. That is only the difference you are going to say. So benzene is a non-linear molecule. So possible fundamental absorption bands is nothing but 3n minus 6. So 3n minus 6 means n equal to here how many? C6H6 12. Okay, n equal to 12 here. So 3n minus 6, 3 into 12 36 minus 6, 36 minus 6 equal to 30. So this is the right answer. So what are the options they have given? That is options A. Okay, so it is going to be the right option. Now let us move to the next question, that is the titration of a strong acid with a strong base. Titration of a strong acid with a strong base, it is represented as first one or second one. That means we know that the value of the graph, it is going to be titration of a strong acid versus strong base. It can be seen as first type. Okay, that already we have read this answer. So these are the different types of the titration curves we are going to observe. So at the equivalence point, the concentration of this H plus ions is equal to the OH minus ions. So whenever strong acid versus strong base is going to be used, that means definitely you are going to see the sharp end point like the curve. Okay, so that's why by seeing the options itself, you can easily identify what is the titration curve related to strong acid versus strong base, because the question is also very easy and you can identify the graph related to the strong acid versus strong base. Weak acid versus weak base means generally you don't get the sharp end point. Okay, whether anyone weak base, if it is there also, you are not getting the sharp end point. Very closely changes are going to be observed at the equivalence point, but only in case of the strong acid versus strong base, a sharp end point it is going to be observed. You can easily identify the graph by seeing the options. Okay, hope you have understood these Gpat 2022 questions. Let us meet in the next session. Thank you students, thank you for attending.